Today is the 9th lecture of this course on process mining, and the topic of today is predictive process monitoring. And with respect to the outline of the course, we kind of are already getting to the end. We kind of have covered the main techniques in the field of process mining and practice them through different exercises. We cover how the topic of business process simulation and how to link simulation with process mining by comparing simulated event logs against as-is real event logs. And now we are going to do something more. We also covered the topic of how to prepare data sets extracted, for example, from a database in the form of CSV files, how to prepare them for process mining. And today we're going to see that these event logs that we have been preparing, the same type of event logs that we will put into a into a process mining tool, it can also be used to generate predictions about what will happen in a case in the business process in the future. And such predictions can have a wide range of applications. So just imagine if the manager of a logistics process, to transport things from one place from one place to another, what will happen if this person was able to see which packages are going to be delivered late tomorrow. That manager could then allocate resources to make sure that that doesn't happen and that the packages in question arrive on time instead of arriving late. The way this is called, this practice of using event logs extracted from enterprise systems in order to generate predictions about what will happen to the future, to the process in the near future, is called predictive process monitoring. And the whole idea of predictive process monitoring is that I am going to take data from the database of an enterprise system, run a number of queries, and extract an event log. Exactly the same event logs that we have been using for process mining purposes until now. From those event logs, we can then construct predictive models using machine learning techniques that are able to, in the middle of a case, like for example, after 3 or 4 events in my process, are able to tell you what will happen by the end of the process. These predictors generate a bunch of predictions for every case of the process, what will happen next. And these predictions, you can display them in a number of different ways. You can display them using in a detailed manner, case by case, for each case, what will happen in the future, or you can build aggregate dashboards from it. And this is actually not science fiction, it's things that are put into practice on a daily basis. For example, I have myself been involved in projects where we build predictive dashboards, for example, for a logistics company, so that the logistics managers are able to know which deliveries are going to be late, or which products are going to be returned, or for example, with a company that does debt collection, this company receives invoices, and they then send this. They then try to get the money out of those invoices. So these are invoices that were not paid on time. Typically, businesses that are like delayed in their payments, and the debt collection agency tries to recover that money, negotiate with those companies to get at least back part of the invoices. And it is very important for them to be able, based on the data in the invoice and what has happened in the past, and based on their email conversations with these different companies that owe these invoices, it is very important to them to know when will they expect to receive a payment, or if they might not receive a payment at all, because if they will not receive a payment at all, then they can immediately launch a procedure to try to recover the money via the justice system. So it can also be used, for example, in the context of an e-commerce process. It's very important in an e-commerce process to understand if a customer will return a product. Product returns is kind of a very important issue. Or, for example, in a hotel booking process, for a hotel booking company, it's very important to know what is the probability that you will cancel your hotel booking, because based on that probability, they can already start like preparing campaigns or discounts to, in case you cancel your booking, to be able to get someone else to get your booking instead of you. So how do we get there? How do we get to the state where in the middle of the execution of a case, let's say after the first 3 events in the case have happened, and we want to know what will be the next activity in this case, or we want to know when will the next activity take place, or how long will it take until the case is finished. This third item is usually called predicting the remaining time. You want to predict how much time there is until my case is over. Another very important type of prediction is predicting a binary outcome of a case. In every process, I said it in the very first lecture, there are outcomes. So a process starts with a needs and leads to an outcome that is of value to a customer. And there are, in that respect, positive outcomes or value-adding outcomes, like, for example, that I deliver the product to the customer on time and that the customer does not return the product, that is a positive outcome. And there are, unfortunately, also negative outcomes, like, for example, that the product is returned back by the customer, or that the product is not delivered on time and I have to pay a penalty to the customer, or that the product is not delivered at all. So there are multiple possible outcomes in the process. And we would like to predict, among many such possible outcomes, what will be the outcome of one particular ongoing case in the business process. So that we call that outcome prediction. And usually in the field of predictive process monitoring, we tackle outcome prediction process in a binary way. Let's say we take one type of defect, like, for example, the customer will return the product that is a defect, and we take the opposite, the customer will not return the product as a positive version. So we have a positive outcome and a negative outcome, and what we want to predict then is a Boolean. Is the customer going to accept the product, or is the customer going to return the product? And then we try to build predictors in the field of predictive process monitoring for that type of problems. One example will be, we will have to pay a compensation to the customer, yes or no. That's a possible type of outcome. How do we do that? How do we predict the remaining time of the case? Or how do we predict the next event that will happen in the case? Or when will the next event happen? Or when will the subsequent event happen in the process? Or how do we predict the outcome of a case? So the approach, generally speaking, is as follows. We will take a historical event log, historical because it contains completed execution traces. And we then will build a Fisher matrix out of it. For every trace in the process, we are going to build a so-called Fisher vector out of it. Why? Because machine learning algorithms typically need these vectors, effectively vectors of numbers. That's what machine learning algorithms crunch. Along the way, we are going to mark, by means of some pre-processing typically, whether a case has a positive outcome or a negative outcome if we want to predict the outcome. We will then take, for every trace, its Fisher vector, and we will construct a table called a Fisher matrix. And we will give this Fisher matrix to a machine learning technique. If we are trying to predict an outcome, a binary outcome, for example, we will use a classifier. If we want to predict the remaining time, or if we want to predict a numerical attribute, such as, for example, the customer satisfaction score, we might use a regressor instead of a classifier, so an algorithm that predicts a number. Sometimes in some application domains, we want to know a little bit more about the future. We not only want to know what will be the outcome or what will be the remaining time, but we want to know what are the most likely pathways in the process from here until the end, because depending on the pathway that we're going to take, then we're going to allocate resources in some way or in another way in order to speed up the process. So we want to have like a detailed description of what will happen in the process from here until the end of the case. And for that, we try to use some techniques called structured prediction, typically based on deep learning techniques. In this lecture, I'm going to keep it at predicting outcomes, classification, and predicting remaining time, which is regression. And I will just briefly mention the existence of techniques that allows you to make predict more sophisticated objects, such as, for example, the remaining pathway in the process. So if you want to build a predictor for outcomes or for remaining times, the most proven method for doing it is this 4-step method, where you first extract a number of sample prefixes of your process. So you take your event log, and the event log consists of, let's say, 1,000 traces, and I start taking prefixes of these traces. Say, from the first trace, I take the first 3 events. From the second trace, I take the first 4 events, etc. So from every trace, I might extract one or multiple prefixes. Therefore, I construct a bunch of prefixes. So let me take as an example this event log, which represents the execution of a process for booking a hotel room in via a website such as booking.com, for example. Every event in this event log represents an action performed by the customer on the website. Like, for example, the first line tells me that Bob used the search box at a given date, and somehow he stayed, he didn't come back for 2 days to the page, and he typed in London. And the same Bob later, he used the function view hotel in the website to see one particular hotel in London 2 days later. And he came back later and he viewed the hotel in Amsterdam instead of London. Somehow later he made a booking for that hotel in Amsterdam, and he paid and he checked into the hotel. On the other side, Alice did something similar, but she ended up actually canceling at the end her booking. For a website like booking.com, it is very important to know whether or not a hotel booking will be canceled, because if it is canceled, then you need to be prepared to be able to replace that customer with another one in order not to lose the corresponding hotel place. So let me first focus on, I'm going to take a pictographic representation of this event log, focusing only on the actions. I'm not going to look at the other attributes. So the journey, the customer journey of Bob starts with a search, and then there are 2 view hotel activities, and then there is a booking, and he pays and she checks in. Whereas the journey of Alice starts not by searching, but she views directly a hotel and she books, and turns out that later she makes a phone call and she cancels the booking. Imagine I have thousands of such observations, or even millions of such observations. In order to construct a classifier out of there, one way or another, the first thing I need to do is to label those traces. I need to find out, based on the data I have in my database, which I I can take during the extraction which traces led to a positive outcome and which traces led to a negative outcome. Or if this was remaining time prediction, well, we need to figure out at what point in time each of these traces finish. Based on that, the first step is to extract a number of prefixes in order to train a machine learning algorithm. So the extreme approach for this is to take all the prefixes. So for example, I take the first prefix, the first trace. So there are two traces in this event log, only two traces. And from the first trace, I can take the prefix with only the first event, the prefix with the first two events, 3 events, 4 events, and all the 5 events. All of them are prefixes. All of them have a positive outcome because that particular case ended up in a positive outcome, meaning the customer did not cancel. The second trace, which has 4 events, allows me to extract 4 prefixes, the one with 1 event, the one with the first 2 events, 3 events, and 4 events. And all of them have a negative outcome. And now I have a lot of examples. You know, I can see that the first 2 events, I can see 2 events, and I can see whether the case that started with those 2 events had a positive outcome or had a negative outcome. And I am ready to kind of start finding patterns in there, which is what the machine learning algorithm is going to try to do. Now, in practice, I'm not going to recommend anyone to extract all the prefixes of an event log. An event log in real might have, for a period of 1 year, might have anywhere from 1 million cases to 100 million cases. And it's not going to be realistic that I then start extracting every prefix of every trace and I start using it for my machine learning technique. So you are going to, at this stage, during the prefix extraction, you are going to have to define a prefix extraction policy. For example, you might choose that you're going to randomly extract prefixes. For example, from every trace, you will extract 3 prefixes randomly, or that you will extract prefixes of size 1, 3, 5, 7, 9, and that's it. You know, you don't keep going. Note that in some cases, in some event logs, some of the traces are fairly large. Like, for example, in the sepsis event log that we have been using in the practice session, there are some traces that have 100+ events, 150 events even. So extracting prefixes of size 100 might be actually overkill. By the way, there is no point in trying to predict when we are close to the end of the case. So you're going to define a prefix extraction policy, and there are multiple options in there to select a number of prefixes from each trace in the event log, so that then each of these prefixes labeled with the corresponding outcome can be put into, it can be encoded for the purposes of applying a machine learning technique. Now I have a bunch of prefixes. And as I told you, the number of prefixes that you can extract can be very large. Of course, you can sample, but the more you sample, the more you might be losing nuances in your data. So you will sample so much, and you might still end up with a heck of a lot of traces. Let's say prefixes, sorry. Let's say 10 million prefixes out there. You can choose to train one machine learning model out of all these 10 million traces. In theory, it sounds nice. In practice, very well-performing machine learning algorithms take a lot of time to train on such huge amounts of data. So it's sometimes very useful to kind of bucket those traces, because they allow you to then train, instead of training one single machine learning model, you train multiple machine learning models, which you can do in parallel. And training with a smaller data set, gives you better performance. And I'm saying a smaller data set, but that smaller data set, which we call a bucket, might still contain 500,000 events each, which is a sufficient number of events to be able to find interesting patterns from there. That's one reason why you will want to split your data set into multiple buckets. There is a second reason, is that you see, predicting the remaining time or predicting the outcome for prefixes that have a length of 2 is very, very different from predicting the outcome from prefixes that have a longer length, like 10 or 15 or 20 events on it. You can imagine with 3 events, there's very little you can do, and your accuracy will not be very high. With 15 to 20 events, you can do much more. And it has been shown empirically that sometimes it does help to bucket your prefixes and to put prefixes, say, that are similar to each other or that are of similar length in one bucket, and separate them from prefixes that are of another shape and put them in another bucket. And then you can now train one machine learning model for each of these trace buckets. So instead of training one single machine learning model for everything, you can train multiple machine learning models for the different buckets. There are different bucketing methods that are recommended or that have been experimentally shown to work well in the field of predictive process monitoring. Of course, no bucketing is always an option. Yeah, that means your machine learning model learns from all the prefixes at once, regardless of their length. For relatively smaller data sets, that can work very well. And in your practice sessions, that's probably what you will be using, because the data sets will not be that large that you need to start thinking about splitting them. Also, the homogeneity of the data is relatively homogeneous in the exercises that we will give you, and it's not necessary to bucket. But when you have messier data sets, larger data sets, you might want to bucket. One simple technique is to take the traces, but only the traces seen as sequences of activities. So you drop all the columns in your event log except for the activity and the timestamp, perhaps. And you put those traces, you see them as strings. Like, for example, you give symbolic names to the activities like A, B, C, D, E. So you have a bunch of traces of the form ABC, ABCDE, ABD, etc. And think about them as prefixes rather than full traces. And now you cluster them using a clustering technique, like, for example, K-Medoids or DBScan or some other clustering, a hierarchical clustering, some whatever clustering algorithm you want to give it a try to. And then out of your clustering technique gives you, say, K clusters, and you are going to then build one machine learning model for each of them, with the advantage that each of these clusters is going to contain sequences that resemble each other. And the machine learning technique is going to, the classifier or the regressor is going to try to find patterns within a more homogeneous data set. There is another way of clustering that can be useful in some cases, which is to cluster per prefix length. The intuition here is that predicting for traces of smaller length is different from predicting from traces of larger length. So I can bucket together all the traces of length, prefixes of length 1, one bucket, all the prefixes of length 2, another bucket, all the prefixes of length 3, a third bucket, and so on. Maybe you go up to 9 buckets or 10 buckets. So you look up to the first 10 events, and you construct 10 different buckets for each length, for each prefix length. And that can work when indeed the length of the trace makes a lot of difference in your prediction. And there are other methods for bucketing out there, some sophisticated stuff where we build like a state machine out of the traces in the event log. And for every state in the state machine, we start constructing, we take all the prefixes that fall in that state, and we start constructing a bucket out of it. Or for every a trace or a set of representative traces, you find the K and N neighbors, and you treat those K neighbors, nearest neighbors, as a bucket. So there are several different techniques, but I would say that no bucketing and prefix length bucketing are perhaps the simplest and the most common to use, followed by clustering. but requires a lot more work from the data science side. So now I have constructed a bunch of buckets. Could be just one bucket of prefixes or multiple buckets of prefixes. And I'm going to train a machine learning classifier for each of them. Now, machine learning techniques like classifiers, like decision trees or logistic regression or ensemble methods such as random forest or XGBoost or CatBoost, or deep learning techniques, if you want to go that way, they require you to give them as input feature vectors. This is like every sample should be represented as a fixed set collection of numbers. So they like to see numbers, 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 numbers. So we need to be able to transform a prefix of a trace. We need to be able to transform it into a bunch of a vector of numbers. So how do we do that? So how do I go from a prefix of a trace containing, say, 5 events, every event contains, say, 20 attributes? How do I go from that to a nice feature vector, a bunch of numbers? So there are, I call that problem, or in the field of predictive process monitoring, we call that problem sequence encoding. We want to encode a complex sequence of events, which is a trace. We want to encode it as a feature vector. And there are multiple methods. It's a little bit tricky. It's a little bit tricky because the prefixes that I'm dealing with, even within a bucket, in some cases, might have very different lengths. There's a lot of null values in there. There are mixture of case attributes and event attributes, and we need to consider all these different cases. Empirically, in the field of predictive process monitoring, it has been shown that there are 3 types of encoding approaches to go from a sequence, from a prefix to a feature vector that work quite well in practice and that are not too difficult to implement. One is the last state encoding. The next one is aggregation encoding, sometimes also called frequency encoding. And the third one is index encoding or index-based encoding. In the last state encoding, the idea is very simple. It sounds like, wow, how can this work? But in fact, it works pretty well in practice. I take a prefix. Sorry, I need to switch slides. For last state encoding, what you do is that first, you separate case attributes from event attributes in the log. I will remind you that a case attribute in an event log is an attribute whose value does not change during the execution of a trace. Say, for example, you have a loan application handling process. Customers ask you for loans. A customer comes, they ask you for a loan. The gender of the customer or the date of birth of the customer is not going to change while you are giving them a loan. So people don't change their date of birth that frequently. Normally they shouldn't, right? Nor their gender, but I'm not going to go in that direction. So the case these are case attributes because their value is basically in practice not going to change during the execution of the case. So for a given prefix and a given case attribute, that prefix will only have one value for that attribute. And then you can easily encode it. If it's a number, you put it in the feature vector. If it's a categorical value, like for example, gender, male or female, then you will encode it as a Boolean, 0, 1. And if it has more than 2 values, for example, the civil status, which can have 4, 5, or 6 values, you will do something called one-hot encoding. So you will put a number of bits, and each bit will encode one possible value of that attribute, and you will have a vector that looks like 1000 or 01000, depending on what is the civil status or the marital status of that person. Now, I said case attributes is easy stuff, piece of cake. Now, how you encode an event attribute? So the event attributes are the attributes of the events in a trace that vary from one event to the next one. They can change values. For example, the activity label of an event is an event attribute. For the first event in the trace, the activity label might be fill in purchase order. The second one will be verify purchase order. The third one will be approve purchase order. So it's changing all the time. So in a prefix, I have a sequence of such values. The resource, the worker who performs the event, who triggered the event, that is also an event attribute. The first event might have been performed by the customer, the second one by a worker called Mike, the third one by another worker called John. So the resource keeps changing over the trace. And there might be other attributes in there that will keep changing the value. Like, for example, the loan amount at the beginning, it might take like 2,000 because that's what the customer wants their loan for. But later, after talking to the credit officer, the customer says, okay, let's make the credit limit 1,500 instead of 1,000 of 2,000. And then maybe later they negotiate that, no, it will be 1,800. So there is a sequence of numbers in there because at different points in the execution of my process, I have different values for the credit limit. So how do I encode that? So the last state encoding tells you, bugger off, just take the last observed value. So just take the last observed activity label in the prefix, the last resource who executed that activity, and the last value of each other event attribute. So you remove completely the sequentiality. You remove, like from the prefix, you only take the last snapshot of it. And then you have a set of values, of scalar values, integers or categorical values, and you can then encode them, just move them into your prefix, into your Fisher vector straight away. The categorical ones can be one-hot encoded, of course. And you may say, wow, how can this work? And I will show you later some experiments that show that it's actually not too bad. It gives pretty good results. It looks like for many real-life applications, for many prediction tasks, just looking at the last thing that happened in a prefix gives you a good idea of what is the probability of a given outcome or what is the remaining time. Just looking at the last timestamp of the last event can already, and the type of event that it is, can already give you a good idea of what will be the remaining time. If you want more accuracy, so sorry, this is an example of how this works. Let me illustrate it to you. So I'm introducing you this because that will give me a basis to introduce you the next ones. This is an event log. This is one event, and this is a trace. And say I want to encode the prefix of this trace that consists of only one event, just this one, nothing more. So a little prefix that consists of one event. So every case attribute will be copied into the Fisher vector and one hot encoded if needed. This one will also be copied here. The last activity that I saw is A, so I copied it here. And the last resources is John. And the case has just started, so I will say that the time since the start of the case is 0, and the last cost is 15. So now let me imagine that I want to encode the prefix consisting of these 3 first events. This is a prefix of the trace number 1. So according to last state encoding, I will take the most recently observed value for the channel, the most recent age. This is a case attribute, I think is this one, 37. D is the last activity. This is the last timestamp. If I subtract it from the initial one, it gives me a duration of 180 seconds. Mari is the last performer, and 10 is the cost. So this third line here, this third row in the Fisher matrix encodes the prefix consisting of the first 3 events of the trace using a last state encoding, meaning I only care about the last event in that prefix of length 3. Very simple. That's going to give me a basis for introducing you a more sophisticated encoding of prefixes of an event, of a trace of an event log, that is called aggregation encoding. So aggregation encoding, what it does is that it does not stop at looking at the last event. It looks at all the previous events in the prefix, but it does not care about the order. It rather looks at all the values it sees for different event attributes, and it tries to aggregate them using an aggregation function, which will depend on whether the attribute is numerical or categorical. So how it works? First, case attributes, that's a piece of cake. The case attributes are encoded into features in the feature vectors, basically one-to-one. They are just transferred into the feature vector. The event attributes, let's take, for example, the activity, because the activity label of an event is an event attribute. It changes over time. So let's say I have seen 3 activities, A, C, and D. Aggregation encoding will do the following. It will put one feature, meaning one column in the feature vector, for every possible value of the activity. If my event log, in my event log, I see 10 different activity types or activity labels, I will have 10 columns in my feature vector, one for activity named A, another one for the activity called B, C, D, E, F, G, H, I. And I'm going to count in a given prefix how many times has activity A occurred. If it hasn't occurred, I will write 0. If it has occurred once, I will write 1. If it has occurred 2 times, because it was repeated, I will write 2. So effectively, I have encoded, I have looked at the sequence of activities, and for a given activity name, I have asked how many times has it occurred. I took the count of that, and I put that number in my feature vector under A. Then I look at the next possible activity label, B, and I look at the prefix, and I see how many times has B occurred in this case? Maybe 0 times, so I write 0. Then I take activity C. How many times has it occurred in the prefix? Maybe 1, so I write 1, etc. I do the same for the resource column. I look at how many resources there are, let's say 25. I create 25 columns, one for every worker in my process, and then I look at a prefix, and to encode it as a row in the feature vector, as a row in the feature matrix, which means as a vector, I say, okay, Sue is, let's say that my first worker is called John. How many times has John been involved in this case? Let's say only in 2 events, so I will write 2 under John. How many times has Mike been involved in the case? Let's say once, so I write 1 in that position of the feature vector, etc., etc. And if an event attribute is a numerical attribute, like for example, the credit limit, then I will look at all the values that this event attribute has taken, and I will aggregate them using an aggregation function that the user may tune, may change. And that could be, for example, the average. If I have seen 3 loan amounts, I'll take the average, but I could have taken the maximum or the minimum or the median. It generally doesn't change too much, and we will typically settle for the average unless there is a specific need to use a different aggregation function. Let me give you an example. I take exactly the same event log that I showed you before. Let me take now the first 4 events. This prefix of this trace consisting of these first events is encoded by this 1, 2, 3, 4, by this feature vector here. Email channel is an event, a case attribute, so I just copy the value of that event attribute for this case. Age is a case attribute, so I just copy it. Now, activity is an event attribute and is of categorical type. It's not numerical, it's categorical. So I look at all the values that this has in the event log. A, B, C, D. There's no E apparently. F, G, H. And I create a column for each of them, a column for A, a column for B, a column for D, F, G, H. And then I look at this prefix and I say, how many times A occurs? Once. So I say 1 here. How many times B occurred? Once. So I write 1 there. D occurred once. F occurred once. G in this prefix here, in this prefix that I have highlighted at the top, G has not occurred, so I write 0, and H has not occurred, so I write 0. The machine experts here in the room will tell me, oh, Marlon, what if I have 300 activity types? And there are event logs that have 300 activity types. I have seen them with my eyes. Will I have 300 features in my feature vector? This is going to explode my machine learning algorithm. So indeed, sometimes you have to make some choices. Like, for example, if you have 300 activity types, you might not want to put into the feature vectors that you construct out of that event log 300 different columns. So you might extract the 20 most frequent activity types and only put those 20 columns and completely ignore all those other activities that are very infrequent. Or you might use some feature selection technique. You might say, you might put them all and then use feature selection to drop some of them. Or you can use something called an embedding, or you can use clustering, by the way, cluster the activities depending on where they occur, but you have to find a way of encoding it for clustering. Or you might use something called embedding. That works pretty well, which means you build a model that in a way tries to cluster them, but knowing in which labels these activities occurs. So it will put activities that occur, in which context they occur, which activity occurs before and after, for example. It's called a word embedding. And you can take from there every character, a word embedding effectively for every character, for every possible symbol, will give you like a class for it. And then you can use that class instead of using the actual activity name. That makes your feature a little bit difficult to interpret because you don't know exactly what that class means. But then you reduce the number of values you have to manipulate from 300 to say 10 or 20. Then I do the same thing for the resources. I see how many resources there are: John, Mark, Mary, Kate. That's it. So I create one column for each of them. And then I take this prefix here. I take this prefix and I see how many times John appears. 1. Mark does not appear. No, sorry, here. 1. Mark appears once. Mary appears 1. Kate appears once. The cost has varied from 15 to 25 to 20 to 10. I might take the sum as the aggregation and just sum them up. So 15 plus 25 plus 10 plus 10, 70. But I could have taken an average. Anything just to extract a piece of that information, to take like an average value or a total cumulative sum, it doesn't really matter in practice, but it's good to take something out of that column into your feature vector. That's more important than the choice of the specific aggregation function. And there is a timestamp column, of course. How do you aggregate them? Well, you transform it into relative times like 0, 180 seconds, blah, blah, blah. The times is the start of the case. And then you apply an aggregation function to this, which could be the sum or it could be the maximum. Might make sense to use the maximum here, anything. So long as you put into the feature vector something that encodes that column, then the machine learning algorithm should be able to do something out of it. And that is how I go from this prefix here, from this prefix of 4 events here, I go to this feature vector. And then I repeat it for all the other prefixes of this event log, and I construct a bunch of feature vectors, which is this table. And I'm ready to give it to a machine learning technique. You may notice that the aggregation encoding doesn't really care, in fact, doesn't care at all about the order of events. In the aggregation encoding, I tell you that A occurred once and B occurred twice in the prefix, but I don't know if it was B followed by A followed by B, or A followed by B followed by B, or BBA. I don't know in which order they occurred. I only know that A occurred once and B occurred twice in the prefix. I don't know in what order. So in some cases, the predictions that you make, for example, about remaining time or about outcome, depend on the order in which the event occurs. So you need an encoding that captures more information, specifically that captures the order. There is an encoding that has this beauty that it is lossless. If you use this encoding, your Fisher matrix contains all the information that was initially present in the event log. In fact, from the Fisher matrix, I can produce back your event log. The price to pay is that this Fisher matrix will now contain more columns, and in real life, it might contain too many columns. So you have to, trim down some of those columns, for example, using some Fisher selection technique. The way the Fisher encoding works is as follows. Case attribute, as I said before, piece of cake. You take the case attribute and you copy it into the Fisher vector as is. For event attributes of type categorical, like the activity, what you're going to do is that you're going to put what was the value of the activity in the prefix at index number 1, meaning in the first position. In other words, which activity occurs first? Say that one is A. Then you have another column that tells you which activity occurred in the second index or second position. Let's say B. Then you have another column that tells you which activity occurred in the third position. Let's say B again. So I have one column for every possible index in my prefix at position 1 or index 1, position 2, and position 3. And I repeat for the resource, which resource performed the activity at position 1, which resource performed the activity at position 2, which resource did the activity at position 3, at 4, at 5, etc. And then I repeat it for every event attribute. So what was the time of the first event, the time when the second event happened in the prefix, the time of the third event, what was the loan amount for the first event, second event, and third event. So you just keep encoding. So you get a heck of a lot of columns, but I'm going to show you some tricks to tackle that problem. So this is how this technique works. Let me take this one, this prefix consisting of the first 3 events of the first case in this event log. That one is encoded by this line, the Fisher vector. So the case attributes just copy it around as usual. Channel age, case attributes become columns in the Fisher vector or Fishers. There is the activity at position 1 is in this prefix is A, so I write A here. The time when it occurs is 0 with respect to the start time. Usually we drop the start time and we encode relative times. It kind of works better because machine learning algorithms like scaled numbers rather than absolute numbers. So I write 0 as the execution time. That's the time when activity A occurred, when the first event occurred. John performed the first activity in the case, John. The second activity was B. It occurred at relative time 80. It was performed by Mark, and its cost was 25 instead of 15. The third activity was D, performed by Mary with cost 10, and that it occurred at time 180. So I encoded this prefix this way. And this other prefix, ADB, well, it's not present here, but this one, the prefix with the first 3 events of A, the third event not being shown, is encoded by this Fisher vector. There is a line here that might be missing, 2, blah, 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 that is kind of not shown here, possibly because of some PowerPoint effect. So Now, warning, index-based encoding gives quite a lot of columns, but it works pretty nicely in conjunction with the prefix length bucketing that I showed you before. Prefix length bucketing, I remind you, is when you take all the prefixes of length 1 and you put them in bucket 1, all the prefixes of length 2, you put them in bucket 2, all the prefixes of length 3, you put in bucket 3. So if you do that, then it works very nicely because every bucket contains prefixes of the same length. For example, I have a bucket that contains prefixes of length 1, and then my Fisher vector for index-based encoding is pretty small in that case. All the vectors, all the prefixes of size 2, I can encode them with a slightly larger Fisher vector, where I have the index 1, index 2 for every column, and I can do the same thing for 3, for 4, for 5. And I might want to stop at around prefix 10. If my event log contains very long prefixes, very long traces like of lengths 100, 200, then possibly I'm not going to use index-based encoding because it will give me too many columns in the Fisher vector, and too many columns tends to kill most machine learning techniques out there. They kill them in terms of scalability, but they also kill them in terms of the accuracy they can achieve because they are unable to exploit all these columns. Although bear in mind that modern ensemble methods like CatBoost or LGBM/XGBoost are able to handle Fisher vectors of 100 to 200 columns, and they do their own Fisher selection internally, basically, implicitly when constructing the trees, and they work fairly well. But with index-based encoding, if you started to encode more and more prefixes of very large size, you will quickly blow up, end up with Fisher vectors of hundreds of columns, and that will not be very good for your machine learning technique. Let me show you how it looks like. If you use prefix length bucketing followed by index-based encoding, what you will do is that you will take all the prefixes of length 1, this one from this case, and this one from the third case, and you will build a classifier for it. And encoding this type of features, once you have reduced encoding prefixes of length 1 using index-based encoding is relatively simple. You will then do the same thing for prefixes of length 2, and encoding them as such prefixes as using index-based encoding as shown here does not lead you to very large feature matrices. And you use this to train a second classifier. Well, finally, the final phase in the workflow for training a classifier or a regressor for predicting remaining time or the outcome of a case is, of course, to train the machine learning model from the Fisher matrix that you constructed in the previous phase of the workflow. And there you can use your favorite machine learning technique. Many of you come from a data science background and will know that there is a trade-off here between simple and relatively interpretable techniques for classification or regression, such as logistic regression or regression and decision trees, and that these techniques are fairly good at providing outputs that can be read, can be interpreted, but they are not very accurate usually. And on the other extreme, you have methods that are optimized for accuracy, but from which it is difficult to extract interpretable outcomes. Although there are techniques for doing that, it's not very straightforward. And that will include methods such as random forest, XGBoost, and its variants, including CatBoost. CatBoost being particularly good in the context of predictive monitoring because it can handle categorical attributes such as the activity name or the resource name fairly efficiently. If you combine the different bucketing methods that I mentioned with the different attribute encoding methods that I showed you, and different classifiers, XGBoost, CatBoost, etc., you get quite a lot of possible combinations for building your machine learning technique. Empirical studies based on a large number of data sets have shown that in this respect, so in this lower is better. So in this diagram, lower is better. XGBoost and random forest tend to perform better than logistic regressions or support vector machines. And particularly XGBoost supports is better to a statistical significant in a statistical significance way than support vector machines. And there's enough support to say that it will be better than logistic regression for that. So my default choice for training a classifier will probably be XGBoost or one of the variants of XGBoost like LGBM, the LGBM implementation of XGBoost, or CatBoost, which is another twist on top of XGBoost. And in terms of bucketing and sequence encodings, there is not that much to know, except that aggregation encodings like these ones, these are all the methods with different bucketings, but with aggregation encodings. Aggregation encodings actually perform pretty well compared to, obviously, last state encodings. Not necessarily better than prefix encoding, but they might be preferable to prefix encoding because prefix encoding has troubles scaling up to large data sets, whereas aggregation encodings are very efficient and can scale up to large data sets. So my default choice for building a classifier for predictive monitoring will be aggregation encoding. And the study shows that bucketing methods in that respect do not matter that much. So my recommendation will be use no bucketing if the data set is small and homogeneous, and consider then using some form of bucketing like a clustering, a simple clustering algorithm based on a string edit distance between the traces. Consider using a clustering algorithm to build buckets if you have a very large data set, which might not be the case in this particular course. The same method I showed you can be used to train regressors to predict the remaining time of a case. In other words, I give you a prefix and you tell me how much time there is until that prefix finishes. All that changes is a bit the technical details, like instead of putting a label for an outcome label for each case, you have to calculate the remaining time from this prefix until the end of the trace and cut it and put it as a label, as a regression label in your data frame for training. Then there are some additional features that you can inject into your feature vector that are very useful for predicting remaining time, and you will see some of them in the practice session. For example, the work in process, the WIP that I have mentioned before, number of cases that are active at a given point in time, is a good feature to inject into your feature vector if you want to predict the remaining time, because remember that the amount of cases that are pending is linked to the cycle time via Lito's law. So lambda is equal to, WIP is equal to lambda times CT, which means that the higher the WIP, the longer will be the cycle times. So it's good to calculate the WIP at a given point in time, inject into a feature vector so that the regressor can find relations between the WIP and the remaining time. So that's just one of the tips that you might want to use when you adapt, when you pre-process data to train a regressor for predicting remaining time. An empirical study based on a large number of data sets has shown that similar results as before, that prefix index encoding is pretty good for predicting remaining time. In this diagram, again, smaller is better. But aggregation encodings end up performing, if you think about it, within the range of error. So there's kind of no reason to prefer here aggregation encoding versus prefix-based encoding. Sometimes prefix-based encoding works better, sometimes aggregation encoding works better. So if scalability is an issue, I will still recommend to use aggregation encoding for training remaining time. You will see in this diagram that there is a technique that apparently performs a little bit better than the others. And this is a technique based on LSTM. LSTM is a long short-term memory. It's a particular architecture used in the field of deep learning. Specifically, it's an architecture of type recurrent neural network. It's a neural network that instead of, let's say, instead of you grabbing a bunch of prefixes and putting them in a Fisher vector flat, what this architecture does is that it takes the prefix of length 2 of a trace, it makes a prediction, gives a bunch of numbers out of it, and it injects what it predicted in order to predict the remaining time at the third event. So you take the prefix of length 2 of a case, you compute some numbers, and together, those numbers together with the encoding of the third event are used to make a prediction of the remaining time after the third event. Then that produces some numbers and you inject them back so that you can make later a prediction when the fourth event arrives, and then when the fifth event arrives, and then when the sixth event arrives. You keep injecting information about your previous predictions effectively into the new predictions. And that combined with the fact that neural networks are able to learn relatively complex functions gives you a little bit of an improvement in terms of accuracy when predicting the remaining time compared to ensemble methods, classifiers built using ensemble methods like XGBoost. The price to pay, however, is that training LSTMs is computationally very heavy. It's actually something you wouldn't do unless you have graphic processing units to do it, because on a regular CPU, it would take forever. So in summary, to train a predictor for predictive monitoring, you will start from your data frame, from your event log, and you will extract prefixes, and then you will do bucketing and Fisher encoding in some order, depending on which type of bucketing you choose. And that will give you a number of buckets. Each of them contains like a Fisher matrix, and you will then give it as input to a training algorithm, a machine learning algorithm, which will produce a machine learning model for each bucket. And then you can then deploy that machine learning model into a runtime monitoring system that will then receive events at runtime. And every time it receives a new event, it finds to which case it relates. It builds the Fisher vector of this prefix of that case that is ongoing, that hasn't finished. It uses that Fisher encoding, gives an input to the predictive model, which gives back a prediction as output. And then you can feed this into some predictive dashboard. This is actually embedded. All these techniques implemented in Python are embedded inside a Promore, but not the enterprise edition you are using, but they are a beta feature in the community edition of a Promore, so in the open source edition of a Promore. But the same code anyway, we are going to give it to you in the lab sessions, and you're going to take the code in Python, and you're going to work directly with that code in Python. We're not going to do predictive monitoring using a Promore. We are going to do predictive monitoring directly using Python scripts or Python Jupyter notebooks. But just for completeness, and so that you see how this looks like, so in a Promore, you can load an event log, of course, and it will extract a predictive model that you can export in so-called a pickle model, a pickle file, as that's the Python encoding of Python objects. And then you can feed it into a runtime component. And the runtime component, when it receives an event, it puts it through a so-called prefix collector. It correlates it with a prefix. And the resulting prefix, it gives it to one or more predictors. One of these predictors might predict the remaining time, another one the outcome. These predictors generate some predictions that are then joined and used to produce a predictive dashboard. To show you more or less how this looks like, let me take here a deployment of a Promore a community edition. This is an event log of close orders. This is what it's like a typical order to cash process. It's a typical event log. It contains only completed traces. I can take this and I can train a predictor with this event log. If I put myself in the advanced mode, you can then select, do you want to use last state encoding or frequency encoding, which is aggregation encoding, that's another name for aggregation encoding, or a combination of these two, or an index-based encoding. What type of bucketing method you have, it could be known. Known is the default, actually. I think here frequency is the default one. What type of classifier you want to use to train your predictor, random forest, gradient boosting, XGBoost, decision trees, etc. You can then say, what do I want to predict? Remaining time or the next activity? Although predicting the next activity is a tricky business, and usually you will only do it using deep learning models because it requires, you get very low accuracy if you don't use deep learning to predict the next activity, but you can do it. You can predict whether the case will finish faster or slower than a threshold, and you can set the threshold. And you can predict any outcome. Of course, for every type of outcome, you then need to define a script below that decomposes, that tells you whether a trace has true for that outcome or false for that outcome. So it doesn't kind of come for free. When I select the delivery type, if I want to predict, for example, the delay rank, I will have to write a script on the backend and put it inside the predictive engine in a Promore to tell me whether a given trace has a delay rank equal to 1 or a delay rank equal to 0. Well, whatever, I could say predict remaining time, and I could ask this guy to train. It creates a job for training the predictor, and I can see the status of the job. When the job is done, I can then go and check the prediction accuracy, so the F-score or the AUC area under the curve of my predictor. However, this kind of can take a little bit of time. Once it is ready, I will be able to download it. I have already here downloaded a few models, predicting models for predicting remaining time, predicting a next event, and predicting one of these outcomes, like whether it will be fast or slow. So I'm going to go back to the portal rather than waiting for half an hour for this model to train, because one of these models will take about 10 minutes to 20 minutes to train. I have already some models already trained. So I'm going to take an event log now containing only prefixes like ongoing cases of a process. Some of these cases have only the first 2 events or only the first 3 events. They haven't finished. And I'm going to create a predictive dashboard from this log of open event logs. So I will select predictively monitor the log. I can create here so-called data flows. A data flow is a bunch of predictors. Like I take a predictor of remaining time, a predictor of a next activity, a predictor of whether the supply rank will be, the delay rank will be 1 or 0. So I can take multiple predictors and bolt them together into a so-called predictive data flow. So I have already one here anyway that contains these 3 predictors. And then I can show a predictive dashboard from there. And the predictive dashboard looks like this. For every case, you will see the number of events, what was the last activity that happened, when did it happen, and you will see whether the case has completed, because this is being done in streaming mode. As the events are being streamed in, this is being updated. And then you will see the probability for those cases that have not been completed, the probability that the case will be delayed, will be quick rather than slow, the remaining time, etc. So let me, so I can see after each event occurs in this trace, I see an update of what is the predicted case end, the remaining time, what will be the next activity, the probability that this order confirmation receipt will be the next activity, and the probability that the case will end up being a quick case rather than a slow case. Here, apparently, all the cases are, well, there are some cases that have a high probability of ending up being slow. If I go to one of the subsequent pages. Okay, so this is pretty much what you're going to be doing in the practice session, but you're going to be doing it straight from Python. Training a predictive model out of an event log. We are going to give you code that already does it, so you don't have to write it from scratch. You have to get that code running, and then you will start adjusting the code, the source code that will give you in Python to solve the different types of predictive tasks and to tune your predictive models. And then you're going to take input data in complete cases, and you're going to feed them in, and you're going to evaluate the accuracy of those predictors that you have trained